Good evening. Being that the Large Collider is in Switzerland, I think we should start right on time. Let me see here. Well, okay. First and foremost, welcome to this lecture series next. These are the experiments that we think are going to be transformative and change the way we view our universe. Last week we saw Dr. Schaefer talk about the next generation of telescopes, and today we will be hearing Elliott Shue talk about colliders that are trying to address the same questions. But before I do that and describe to you a little bit about Elliott Shue, let me thank our underwriters. As I've mentioned before, this is actually an expensive operation to bring to all of you, and Cox Communication and Bob Davis, who's been a very good friend of the College of Science for many years, the Galileo Circle, who are the members of our community that support the College of Science, Godat, who makes these beautiful designs, Tom and Candy Grogan, Jeff and Shelley Owen, Raytheon, who's been a partner with us on this for a while, Research Corporation, who that actually gives us money so that we can pay the tuition of middle school and high school teachers to come to these events and get credit for it so that they can get, as it were, retooled with these new kinds of knowledge, and Unisource Energy. Thank you very much to all of you for supporting us. Now, it's my distinct pleasure to introduce to you Elliott Shue. He's a professor of physics here at the University of Arizona, and he's also the Associate Dean to the College of Science, my partner in crime. He's part of the international team working on the Large Hadron Collider, the extraordinary international research project, and one of the largest scientific experiments ever conducted that you will be hearing about more this evening. Elliott's research focuses on searches for supersymmetry and a new phenomena at the Large Hadron Collider. Elliott received his PhD from Cornell and then went on to the prestigious Robert McCormick Fellowship at the University of Chicago. Then he realized that he was really smart and he left the cold, and he joined the U of A faculty in 1996. Following tonight's lecture, Nick Wolf, professor of astronomy, will give us a sneak preview of next week's lecture. But now, please welcome our special guest, Elliott Shue.
Thank you, Joaquin. That was very nice. Today, what I'm going to talk about is the Large Hadron Collider and how we will be able to use it to look at the next, or understand matter at a much deeper level. The Large Hadron Collider you can see over here is a device that sits underground. It goes about 100 meters underground, and it spans the border between France and Switzerland. This is one of the components that's going in, and just to give you an idea of the size, you can see people as they're trucking this large magnet across the roads separating one part of the CERN laboratory from the other, and as they're bringing it across the road, they're going to drop it down this large hole and hopefully install it correctly. You can see actually as they started to put this detector together, you can see the large components that are being put together, and you can see this couple of people up on a crane putting it together. But before we do that, I wanted to give you the particle physics primer. In order to understand what we're doing, we have to have Physics 101. And first of all, you have to get an idea of what particle physics is. Particle physics is going to try to answer the following questions. What are we made of? What are the most basic particles? So there's the particle that comes in. And what are those basic particles, and how do they fit together? And what forces actually govern those particles? Those are actually the main questions, and what we'll try to talk about today is what is the origin of mass. So in the 1900s, people started to realize that particles, that things were made of smaller and smaller particles. We first started off and maybe understood that there are molecules and atoms, And in the early 1900s, Ernest Rutherford started trying to shoot particles at other particles. So that was kind of the very first beginnings of what we now consider modern particle physics. And when he did that, he found that things scattered off at angles that were surprising, because it turns out that inside the atom is a very hard core called the nucleus. Well, as people have started to understand more and more, that nucleus is made of things called nucleons. And nucleons are just protons and neutrons. And then in the mid-1900s, people realized that even those particles were made of even smaller particles called quarks, which you may have heard of. And now as we start to, in the beginning of the 21st century, we're starting to look for other things, and could there be smaller and smaller particles? So in order to do this, it's going to require special tools, and that tool in our tool chest is the Large Hadron Collider. So it turns out that there are just 4 forces that we know of that we can understand, and these forces are gravity, which is the thing that Newton's apple found. It's just the thing that massive bodies attract each other. Electromagnetism. Electromagnetism is the force that gives rise to basically electricity and magnetism, but it does more than that. It actually allows things to not fall through the floor. The thing that's the force that holds material together is electromagnetism. There's a strong force, which is the force that actually holds this nucleus together, because the nucleus is made up of protons and neutrons, and the protons have electromagnetic force, which would repel them apart. So the nucleus would actually fly apart without the effect of this strong force. And finally, there's this thing called the weak force. This is the force that powers the sun. And it's actually an interesting story, because it turns out that people at the very beginning of the 20th century, didn't understand what force could actually power the sun. And one of the proposals was that the sun was powered by gravity. But it turns out if you actually powered the sun with gravity, it would only have lived up until about the early 20th century, about 100 million years. And from other sources, people actually know that the Earth is about 4.5 billion years old. So there's a problem. The problem was resolved when people actually started to understand there's this extra force called the weak force, and it was kind of confirmed when Ray Davies actually discovered neutrinos coming from the sun, which showed that the force that powered the sun was this thing called the weak force. We also know something else. We know about the matter. The matter that we know of is that all things in the world now, in the universe, are made up of 2 types of matter, things called quarks and things called leptons. The quarks, we know, respond to each other through the strong force. And things that are made up of quarks are things like neutrons and protons. And it turns out that anything that's made up of quarks is called a hadron, hence the name the Large Hadron Collider. The other type of particles are leptons. These are particles that respond to the electromagnetic and the weak forces. And the familiar lepton that you all know about is the electron, or at least you've probably heard about it. The other leptons are the tau and the muon. And we'll see a little bit more of that. So all that stuff is what we call the Standard Model. It's a standard model of particle physics. And that's it. That's what we know today about the Standard Model. And it turns out it's very precise. In fact, it's extraordinarily successful, because with this Standard Model, which is just the forces and the particles, we can actually describe all of the particles that exist in the world and new particles that we've been discovering over time. And in fact, Richard Feynman once said that the Standard Model is so precise that it's as if you could predict the distance between New York and Los Angeles to within the width of a hair. Yeah, so, sorry, let me go back. So yes, that's very precise. However, every recipe has many recipes ends up being problematic. Our recipe, turns out, has one problem. It turns out the Standard Model, the masses that go into the Standard Model are put in by hand. They are actually not inherent in the model. And so because of this, we can't explain why there are masses in the model at all. Well, in the 1960s, along came this guy named Peter Higgs, and he, again, asked the question, why do things have mass? And he proposed a solution. That solution has been called the Higgs mechanism. And it basically says that there's a Higgs field permeating all space, and as particles move through it, they acquire this thing called mass. And the resultant aspect of that is that if there was such a thing called the Higgs mechanism, there would be a particle called the Higgs particle, which many of you might have heard of. And so actually what we're trying to do at the Large Hadron Collider is actually look for this particle. If we discovered it, we'd actually be able to understand and describe why mass occurs. So the question of mass then can be answered by this next generation of physics experiments, specifically the Large Hadron Collider. And as you've seen in the first picture, this is actually the largest particle physics experiment to date. The tunnel, as I'll describe in a second, actually has a circumference of 17 miles, and as I said, it spans 2 countries. And in particular, the signature for these Higgs particles will be striking. Here's an example of what we might actually see in our detector. This is a simulation of a Higgs particle as it is produced and then decays inside one of our detectors. And I'll describe this a little bit more, but basically these sprays of things that you see coming out are some of these fundamental particles which are produced as the Higgs particle decays. So you may or may not be familiar with this equation. This is Einstein's famous equation. And what it says is that energy is related to mass. And the relation between energy and mass is because it comes through the speed of light. I've written down the speed of light is 300 million meters per second. And if you square it and multiply it by the mass, that means in order to produce a particle of a given mass, you have to have an enormous amount of energy. And that enormous amount of energy can only be provided by very large machines. As a corollary to that, it turns out if you want to study things that are very, very small, you need a lot of energy. And you can kind of see that when people first developed their first microscopes, they could use regular light to shine off the particles and see what's reflected back. But as you want to probe deeper and deeper inside in smaller scales, you need something like a scanning electron microscope, which uses more energy. So that's the end of your primer, okay? But you actually have a quiz. You'll have to tell me what this equation means at the end. So this is the machine that we're going to use to look for those things. We're going to try to look for these Higgs particles. The LHC spans, and I'll show a better picture in a second, actually consists of a number of different accelerators. And if just off to the right, you can actually see the Geneva airport. So that'll give you an idea of the scale. And again, in some sense, you can think of this as a gigantic microscope. Here's a slightly better picture. And what I can show you here, here's my mouse, is you can see this is the Geneva airport here down at the right. So the Large Hadron Collider is actually bigger than the airport itself. And what you can see is that this dotted line, I don't know if you can see it very well, but this dotted white line which goes around is actually the border between Switzerland and France. So these particles are actually going around the ring and crossing the border many, many times throughout its route. I wanted to just give you a brief overview of actually how long we've been working on this thing. In 1984, the first feasibility studies for how to build this machine and bring it to fruition were started. This machine was actually envisioned as a competitor to the Super Collider, which was to be built just down the road in Texas. After it was canceled, this became the premier place to do particle physics. In 1992, there was a proposal, so about 8 years later, for actually building a detector. The experiment is actually one of 4 detectors that is going to be located in the collider, and I'll talk about what you need these detectors for. The University of Arizona joined about 2 years later. It turns out that Mike Shoup and John Rutherford, who are 2 professors in our physics department, had been working on the SSC, and they actually heard the news of the cancellation while they were at CERN doing some tests. So they actually walked across the cafeteria to the leaders of the Atlas experiment and said, hey, can we join? And they were welcomed with open arms. In 1995, the experiment, this Atlas experiment, was actually approved. And here you can actually see the first approval on this letter. What you can see here is coming down is, remember that this hole, the collider sits in, is about 100 meters underneath the ground. And this is looking up the access tunnel where they have to lower everything. So every single piece of the equipment comes through just a few access tunnels. In particular, this is one of the big magnets that is used in the collider. It actually has to be brought down, and then it goes down one of these halls throughout the tunnel, and it's just shuttled along by little carts until it's brought into place. And the last magnet was installed about 2 years ago. And then the construction of the whole collider, including the experiments, the Atlas experiment in particular, was completed just last year. So in order to see what a collider is, you have to kind of understand that there are a few components that make it up. Remember, what we're trying to do is we're actually going to take a bunch of protons, and if you look here, they're going to be injected in these 2 regions. Some of the protons go to the top, and some go to the bottom. And these protons circulate throughout this tunnel and then collide at certain spots. In order to get a proton that's moving with so much energy, to move it in a circle, you have to have magnets, these blue and white boxes, that will actually bend and focus the protons so that they can actually hit each other. And then you have to be able to provide some energy to them so that they don't just all peter out. And that's done by these RF cavities, these orange structures. But then all you've done at that point is you just created two beams of protons going in opposite directions. You need to bring them together in certain spots so they actually collide and give you that energy from the E equals mc squared. And that's at this red spot called a detector. And the detector actually is looking for the byproducts or the decay products that occur from that collision. So what we hope to happen is that the two protons collide, they produce enough energy to produce a Higgs particle, and that Higgs particle will actually decay into something that we can see. And here's just showing one of these magnets. These magnets are actually used superconducting wire, which has some issues, and I'll talk about that later. And they're about 30 feet long, about 9.5 meters long. And there are a few thousand of them. I think there are about 1,200 or so of these magnets all throughout the ring. And here's just a picture of one of these RF cavities, which are used to give the protons energy to get them up to these high energies. So what I have here is a little movie. What you'll see is that the collider complex is made up of a series of rings. Each of them is a little accelerator, and as we go around, what you'll see is a red dot, which is meant to simulate a proton. The proton will get accelerated here, it'll get accelerated more through the bigger ring, it'll go through another ring, and finally it'll go into the big ring, which is the LHC. And then at some point, we'll send another beam of particles in the opposite direction. They'll collide, and we can make them actually collide inside these detectors. And the detectors, by looking at the byproducts, should be able to tell us what's going on. So here you can see this red dot as it circles around. It's now in the smallest of the accelerators. It then goes into the slightly larger one. Now it goes into the final one. But at the same time, at the bottom, there's another beam of protons that are going to go into this ring also. And eventually, one of the bunches will go in one direction, the other will go the other. And they race around. It turns out that they don't always collide all the time. There's some probability that some of the protons will collide. When they do, you'll see that they actually come into the detector, they hit and collide, and you get this spray of stuff coming out. And by looking at that spray of stuff, we can actually tell what's going on inside the detector. So here's just to show you what the detector would look like if we now delve down under the ground. We're going to go down about 100 meters down. The detector is sitting inside this large cavern. And as we break open this cavern, you'll start to see that this detector is this very large device. And here's a cutaway. You can kind of see a person will come in. The silver thing going through the middle is actually where the beam of particles goes through. And it's only about 6 inches in diameter or so. It's a very small device that's going the 17 miles all the way around. As you zoom out, this actually shows you what the scale of this detector. This is one of the 4 detectors called the Atlas detector, which is the one that the U of A has been working on. So what I'd like to do now is show you actually how these particle detectors work in the sense of what is it that you're going to see that can tell you why you know what happened in the middle. The ring in the middle, if I can here, this ring in the middle is a beam pipe. It's a cross section, so you've cut it in half, and that's where the 2 proton beams actually collide. So what will happen is that once they collide, you can see particles coming out, and what you see here is a cross section of the detector. The detector is built like an onion, so there are different layers. The inner part of the detector consists of parts that actually measure charged particles. So particles like electrons, things that have charge on them, are measured in the very intersection, and those parts actually will bend inside the magnetic field. Then outside are the orange section and the blue section are called calorimeters, and they measure energy. What happens is that the particles actually create a shower of secondary particles, and by measuring the energies of those particles, you can tell what happened inside the detector. So there's an orange calorimeter called the electromagnetic calorimeter, and then the blue one is the hadronic calorimeter. So particles that respond to the electromagnetic force, i.e. leptons, respond most heavily in the orange section, and particles which are hadrons, like protons and neutrons, respond in the blue section. And then these very, very heavy leptons called muons make it all the way out. So as we'll see here, oops, sorry. You'll see here, this is an electron going through. You see it bends a little bit in the intersection and then showers inside the orange section. A photon's going to come out next. It doesn't bend inside in the early section because it doesn't have any charge, but it also showers in the orange section. Now here comes a proton, and you'll see it actually bends in the opposite direction because it has the opposite charge of an electron, and it showers in the blue section. And a neutron, which has no charge, goes straight, but also showers in the blue section. And then a muon's going to come out, and it's going to curve in the same direction as the electron because it has the same sign charge. They're both negatively charged. So what we can do with this is by looking at the signatures of a particle interacting inside the detector, we can actually identify what type of particle it is. And by using that identity, we can then infer what happened inside the beam pipe where there is no detector. So just to give you an idea what the numbers are, here's the size of the ATLAS detector. This is just the detector, not the collider, and it's about a half a football field long, and it weighs about 7,700 tons. So if you took 100 empty 747s and weighed them, that would be about the weight of the ATLAS detector. We're actually going to produce about 3,000 terabytes of data a year, and if you took a stack of CDs and stacked them just on top of each other, took those little round cases, you get a stack that's about 4 miles high just from CDs. The energy of this is very energetic. So the reason we have to build such a big machine is to get such high energies. And if you were to take this energy, which is in some units called trillion electron volts, and converted it to a temperature, it would be a temperature of about 100,000 times the temperature of the sun. We're going to collide about 1 billion collisions per second. And this, in order to build such a large device, you can't just have 20 of your best friends. You actually have to have a group of people who have some expertise in doing that. And that includes a group such as this. This is actually just a small fraction of the people in one of the buildings. You can see there's quite a large number of them. We actually don't have a picture of all 2,500 physicists. So the University of Arizona has been involved in this experiment almost from the very beginning. And I'll show you some of the things that we've helped build and where we're going to go and what we're trying to do with it. So as I said, there are these calorimeters. These calorimeters are filled with liquid argon, which is a noble gas. And by looking at the response of the particles in that, again, we can measure their energies and use that for identification. And the University of Arizona has been responsible for this thing called the forward calorimeter, which is this kind of copper-colored object right in the very forward region of the detector. And what I would like to emphasize is that the U of A has had a really important role in the experiment from the very beginning, because when the experiment was first designed, it looked like this. And what you can see is that these big red cylinder shapes at the end were the first design for the forward calorimeter. When the U of A joined the experiment, we did some studies and realized that, in fact, by putting those calorimeters where they are, it would render large fractions of the rest of the detector inoperable because of the splashback of radiation from those detectors. So what the U of A did was actually design a better forward calorimeter, and now the forward calorimeter is this region in here, this green section, which is well inside the detector, where, one, it can absorb the rate, but also it doesn't have such a detrimental effect on the detector. And so this design was chosen by the collaboration of this now 2,500 physicists and found to be the one that actually works best. Here's actually a picture of the construction of it. The calorimeter is made up of this big copper matrix, and inside the matrix is a single tube, and down the region between the tube and the matrix flows this liquid argon. You can see one of our techs, Ken Green, actually putting it together. It was actually built here in the basement of the physics building, oh gosh, almost 10 years ago now, as we started to put it together. And then we had to crate it up and move it out of the basement. So here you can actually see in the back of this picture, you can see the Gould-Simpson building, and this is the region between the two halves of the physics building. You can see them bring it out of the basement and loading it onto a truck. Then it was put onto a boat and moved all the way out to CERN, and then they dropped it. They actually had a forklift operator try to pick it up, and it was after lunch, and it's Switzerland, and so they dropped it. And you can see on the lower left picture, there's a yellow bar. You can see it actually bent it. That's actually an iron bar, a steel bar that actually bent after they dropped it. However, we picked it up, refurbished it a little bit, and this is when we actually installed it. So it turns out that even after all that rough handling, that it was actually not too bad. They were able to refurbish it, and things weren't too bad. So it's actually now an integral part of the ATLAS detector. The other aspect that we're working on is some of the muon detectors. Remember, these are the detectors way at the outside of the detector. And remember, our muon is just a heavy electron. And this, again, we're concentrating in what we call the forward region, or the region in the very inner part of the detector. And we've been developing some instrumentation. Here's actually a group of our physicists out at CERN, happy that we're actually having installed things. What you can see are these chambers on the top left, are these brown objects. These are actually chambers. We have one in our lab upstairs in the physics building. And we developed a lot of instrumentation for it, which will allow us to have these chambers achieve their ultimate precision for detecting where the particles went. Here you can see them actually putting these, what we call the CFC chambers, in their frames. This frame is about 30 feet across, so it's very large, and you have to have a crane to actually get them up there. And here you can see them actually dropping that whole structure, which again, it's about 30 feet across, down this access tunnel about 100 meters down into the cavern where it's going to be installed in the Atlas detector. So one of the big challenges of something like this is we have a huge amount of data. Just like the LSST experiment described last week, the current experiments that people are designing and building, or the next generation, produce huge amounts of data. And then the question is, what do you do with all that? So what we do is brute force. We're not that smart. So what we do is it takes about 15 seconds to analyze an event. And so we just get lots of PCs. The PCs are deployed throughout the world. And what we do is we ship off fragments of our data, have the PC crunch on them, and then bring it back. And that's actually called grid computing. And that was developed in conjunction with a CERN laboratory. And here's just one of the data centers that are used to analyze the data that, as the data is coming directly off the experiment. So the experiment goes into a computer, gets analyzed at some fraction, and then written directly to a tape or a disk. So we have been involved in some of this aspect. Some of the things that we've been looking at is looking for these Higgs decays. We also have a group here that's going to be looking at topped quarks and other exotic decays. And as I showed before, this is actually what you might see in your detector. Remember, you have a Higgs particle coming in. It decays inside your detector and produces these big splashes of particles that are coming out. But that's not the whole story, because at the end of the day, you'd like to publish. And what are you going to publish? Well, and this is a plot where on the horizontal axis is what is the mass of a reconstructed particle. We're going to look at lots and lots of events that occur in the detector. And over time, what you'll see is that a bunch of crosses that accumulate with time. Those crosses tell you how many events occurred at a given mass. And as I start this forward, you'll see that it's hard to tell that anything's going on even after about a year. But as you go through about a year and a half, and finally hit even 2 or 3 years, what you'll see is this peak occurring in the mass. And if you were able to see such a peak, you would probably, or at least be in line to win a Nobel Prize, because that would be consistent with seeing a Higgs particle. So everybody does surveys. They were very popular last year, especially around November. And one of the surveys that was done, actually this was done before that, was to survey particle physicists and ask them what they're going to see at the LHC. And you can see that it's actually kind of mixed. A lot of people would like to see the Higgs. Some people say we might see something unexpected, and some people say we might see nothing at all. But nobody knows. So, that's why we do the experiment. That's why people play the Super Bowl. One thing that we hope to do is to search for dark matter. And dark matter is actually, there's quite a bit of evidence for it, as you saw in last week's talk. This is something called the bullet cluster. The bullet cluster is actually the collision of 2 clusters. And what you can see in the red is ordinary, what we call baryonic matter. So that's the stuff that we know about, these quarks and leptons. All that stuff is basically what we call baryonic matter. And then the blue stuff is evidence of dark matter. And the reason people think it's dark matter is that, well, first of all, as these 2 galaxies collide, the dark matter and the ordinary matter separated. And then the dark matter region, these blue and purplish sections, when you look at the galaxies behind them, they actually look like they are distorted. And that's because the light from those galaxies, as they pass through the dark matter, gets distorted and bent so that you actually see a different shape. Well, turns out this dark matter makes up about almost a quarter of the whole universe. The thing that we know about is the 4%, that 0.4% stars and 3.6 intergalactic gas. And what's actually interesting, if you went back 100 years, the only thing we knew was the 0.4%. And now, after, I guess, 100 years, we know 10 times more, but we only know 4%. There's this dark matter out there. And the astronomers can tell us that there's lots of it, and they can even tell you where it is. But the LHC, we hope, will actually be able to tell you what it is. And that's what we hope to do with this experiment. So on September 10th, it was actually a very exciting time. I stayed up, it was about midnight here in Tucson. They actually sent protons all the way around the LHC. Now, they only sent them in one direction. And in doing that, it was quite a celebration because it's the first time they proved that they could actually get the machine to run. And it only took them an hour to send protons from the starting point all the way to the end. Now, that sounds pretty slow for something that's supposed to be moving at the speed of light, but they did it as a function. They only did they did a segment at a time. So it took them an hour to make it through. Once they did that, of course, the protons were moving at the speed of light. And this is a picture of actually what the ATLAS detector saw when that first beam of particles went through. What they did was they allowed the beam of particles to hit what's called a beam stop. And as it hit the beam stop, it produced a huge spray of particles, which could be seen in the detector. And not only was it a good time, a success for the LHC, but it was also a success for all the detectors because you can now show that these detectors will respond appropriately to large amounts of energy. But that's not the whole story. 9 days later, you probably heard the LHC suffered a severe accident. It turns out that, like everything, it's the smallest things that always matter. In this case, there is a weld between the two magnets. It's a superconducting magnet, and between a quadrupole and a dipole, two of these types of magnets, the weld was actually faulty, and it became non-superconducting, and it arced. Well, the arc actually punctured the helium enclosure, which is what keeps this thing superconducting. And that helium explosively expanded and basically destroyed the magnet. And you can see here on the left-hand side that this is supposed to be straight. You're not supposed to see this kink. And these are two very large multi-ton objects that got moved by this explosion of gas. And this is the concrete mount that it was mounted on. You can actually see that the thing actually got destroyed. And here you can see somebody looking quizzically at what happened. So it required removal of about 53 magnets. Now remember that they put down a few thousand magnets in the process, but what happens is that the magnets have to be taken all the way up this big tunnel, cleaned, and then tested. And that process of testing each one takes weeks, and the facility they have to test it can only handle a few magnets at a time. So the reason that it takes a long time to do this is not because they can't do it quickly. It's just that they don't have the ability to do it in parallel. And so we're expected to restart the machine this coming summer. So the excitement's still there. We're just off about a year. So what next? Well, the first beam, as we said, occurred about a year, 6 months ago. And we now expect that we're going to have collisions of the particles this summer, followed by results coming in the winter. And hopefully, after that, we'll actually see evidence for the Higgs particle. But of course, nobody can predict when that will be. Well, I'd like to talk also about some of the other aspects of particle physics. We do it because we love the science, we love doing research, but there have been lots of actually very beneficial spin-offs that come from doing the science. One of them has been, here you can see a man sitting in a proton cancer machine that actually is one of the more precise ways to treat cancer, it turns out. And this is basically just a small proton accelerator, which is a directly spin-off from the technology that was developed for this kind of research. In fact, the first proton accelerator for medical research, I believe, was developed at Fermilab just outside of Chicago. Another thing that you may have heard of is this thing called the World Wide Web. It was actually developed at CERN, this laboratory, to help the scientists communicate with each other. So it was a way for people to share documentation. And what you can see here is a picture of kind of the interconnections of the web across the globe. And so you can kind of think of it as our gift to you, for better or for worse. Anyway, so that's one of the aspects. But one of the other things that's interesting is that one never knows what's going to come of what you're looking for, because research has all kinds of broad implications. This is an article from the New York Times when Thomas Edison first announced the invention of the light bulb. And you can see highlighted in yellow that there were some skeptics as to its utility. So some of the other things that have come out of the LHC are these large superconducting magnets. People have, of course, made superconducting magnets for a long time, but what we've been able to do is show that you can make them very, very large scale and lots of them. And also this grid computing has come out. Of course, if you look back in time, people have always been looking for these types of things. When people looked at the electron, it basically was parlor tricks. In the late 1800s, people were using static electricity to play with, and then some bright people got the idea to actually try to see what these particle things were. And of course, the electron has led to a huge list of things which have had, I would say, many benefits to society. One of the things that has been in the news quite a bit, which you've probably heard about, is the production of black holes. This is a simulation of what a black hole might actually look like if it were to occur inside the LHC. So actually people have thought about what could happen, and what everybody basically agrees is that if you were to produce a black hole inside the LHC, it would evaporate immediately, that it wouldn't have enough mass, basically, because all you're doing to produce that black hole is basically bang two protons together with very little mass, and even though it's a lot of energy, it's not a huge energy density. And so we expect that they would actually evaporate quickly, but there are actually other evidence that these things probably don't exist. And the reason is because there are lots of these things called neutron stars out there, which are bombarded constantly by cosmic rays. And those cosmic rays have enough energy to produce the same exact black holes, and if these black holes were destructive, those neutron stars would have been eaten up a long time ago. And the fact that we see these neutron stars is evidence for the fact that they probably don't exist. So as I come to the end, I just wanted to show you that we have a fairly large group of people. We have a group of faculty, staff, and in particular postdocs and students. We're actually looking for a few students, so if you're interested, give me a call. And we've also had a huge number of undergraduates, and here at the U of A, undergraduate research is really something that we treasure and value. And here's just a host of the people that have been involved in that endeavor. And in fact, I should say that a lot of them actually have made it out, a large number of the people pictured actually made it out to CERN and helped us to integrate the detector into the ATLAS detector. So before I go, I just want to say that it's been a real fun experience, and here's a stop-action film of the construction of the ATLAS detector as it was being built. I should note that everything that's in there had to come down this large access tunnel, and so even that crane had to be lowered down and then raised back up. And there's another problem with it is that that things had to be done in a jigsaw puzzle way. So we actually had to lower parts of the detector first, move them off to the side as we built the rest of it. And you can see that here, this, at the very end, this part of the inner detector was built off to the side, it's lowered in, and then they started bringing these very, very large toroidal magnets, and then you can see them assembling them. What I like to say, though, is that it's been a very interesting and great endeavor that we've been doing, and the U of A has really played a very integral part in this whole endeavor, and what we hope to do now is actually see the results of those efforts, and hopefully they'll accumulate in something very exciting. Here you can see the last of these toroidal magnets being lowered into place. You can see them put them into place. They have to have some extra structure, and now you can see the inner detector being slowly winched into place into the middle of the detector. And once it's fully in, the detector is finally complete. So that's what it is. So I'd like to thank you very much for your time, and I hope you enjoyed that.
Thank you, Elliot. I'd like to introduce Nick Wolf, professor of astronomy. Nick was the brainchild. Well, he was the one that decided we should do this as a College of Science. So we've had a whole bunch of lecture series, and he's the one that's been running everybody ragged, getting them together for all of you to see. So thanks, Nick.
Well, this is a chance to ask questions of Dr. Chu, and I'm going to take advantage of my position and ask the first question, because you talked about the temperature of the sun. The sun is hot on the outside and very hot on the inside. Which one is it that this is 100,000 times hotter than?
I believe it's the outside temperature. I believe that's true.
Okay, next question, please.
What was the cost?
There's a microphone.
What's the cost of putting the collider together, approximately?
Actually, that's a good. I was going to look. I forgot. Well, there are two problems. One is that it was done in Swiss francs, and I believe I'm going to give you. I can't give you the right number off the top of my head, but it was a lot. I thought.
with 1,000 magnets, why are you only inspecting 53 of them for welding seal failures?
The reason is because it turns out that, well, one is that to some degree they were all tested during the process of bringing it up. The other is it turns out that it's very cost prohibitive to actually go through and look at they're inspecting everything, but they're not going to bring all the magnets back up to the surface to test them. So they're going to try to do a lot of the testing in situ. But the 53 magnets that they're talking about actually have to be raised all the way to the surface, opened up and cleaned up, and then tested and they have to bring them up and down. What actually, after the accident, I believe they also did a lot of testing in situ of what had not been turned off yet.
If you did want to create a small black hole, how could you do it safely? And how much mass would you have to?
Well, I guess it wasn't so clear, but in fact, there's some possibility that we would create a small black hole in the detector. And what you saw was the result of this black hole actually disintegrating in the detector and producing all these standard particles that we know about. So in fact, if they do exist, they would be produced in the detector, and they would be safe. Now, the reason that you have to be a little skeptical is that these theories that predict these small black holes actually haven't really been shown to be viable yet. And they actually predict that they predict that the strength of certain things would be higher by 30 orders of magnitude, and we don't see that. So because of that, it's very unlikely. But even if they did get produced, because of the total small amount of mass that's used to produce them, they would be safe anyway.
So if you did want to make one, you'd need a bigger collider in order to get enough mass?
No, I mean, we actually will possibly produce a microscopic black hole. We could, but it won't actually have very much effect inside the detector.
Because there's no mass.
Right.
Okay.
How are you going to dissipate the heat that's generated in these collisions?
Well, the heat it turns out that temperature and heat are somewhat related, but the heat is more the energy. And even though it looks like the temperature is very hot, the amount of heat is actually very small. The amount of the energy is big compared to the mass of the proton, but if you look at even the total current inside the machine, so if you take the protons and look at the amount of current that's in that beam, it's something on the order of amps, or an amp or so, half an amp or something like that, which, if you look at what's inside your wall, there's usually a lot more current than that.
At what temperature do the superconducting magnets superconduct?
Well, they're running at liquid helium temperature, which I believe is about, 2.3 or so degrees Kelvin. So they're actually running close to absolute zero.
We lived in Texas at the time the superconducting super collider was being built. Could you do a little compare and contrast what that was going to be?
So the SSC, the superconducting super collider, was about 50 miles in circumference, and so this machine is about 17 miles in circumference. So it's actually smaller than the SSC. The difference is that the LHC is going to be at a lower energy, so the energy of the two protons colliding is much lower, but they're going to put many, many more protons than in the SSC. The SSC, they were going to operate at much higher energies, but at lower rates. So the LHC is going to gain by doing things much quicker, whereas the SSC is going to do them at higher energies.
Recently, there was an article in one of the science magazines about something sort of like a wave rider, where the particles ride a plasma wave, and in about a foot or two can get the same kind of energies that the LHC can. How was some of that work affecting what you'll see out of the LHC?
Well, believe it or not, even though we're just starting up the LHC, we're just about to start doing, they're planning and actually building upgrades for the LHC. Now, the plan is mainly to increase the interaction rates, so the number of protons that can hit each other. But where that kind of research is going to go is for the next generation of accelerators that would come after the LHC. One of them is called the Linear Collider, where there's some proposals to build one either here in the United States or in Germany. So one can imagine that maybe technology like that would actually help in that realm.
On the supposition that you don't find the Higgs boson, in your opinion, what's the next best explanation for the mass of the particles?
That's a great question. Actually, I don't have one. I'm hoping it's the Higgs. But you know, there are actually lots of different things that people are looking for. Another thing that is very interesting is something called supersymmetry. And so when I talked about these dark matter candidates, it turns out that supersymmetric particles could, in principle, be used, could have a lot of the right characteristics to explain dark matter. They occur at the right rate and explain a lot of the cosmological things that people see. So if it is, so that's actually one of the other things that people are desperately looking for. It turns out that the theories break down at the energies of the LHC. So if there isn't something like the Higgs particle, there must be something else to explain the theories that we have. Otherwise, they wouldn't work. So there's something exciting going to happen. We just don't, and we hope it's the Higgs, but it could be a few other things too. There are lots of different theories that people have out there. Supersymmetry is one, Technicolor, all these other things that people have talked about.
Even with the tunnel of about 6 inches wide, I believe you said.
Right.
The probability of these protons, extremely tiny protons, actually colliding is extremely small. Is it just that accurate to be able to get the protons to collide, or are you simultaneously sending a large number of them at the same time?
No, that's a great question. So it turns out that the beams of particles, we actually don't have one proton going at a time. We actually have bunches of protons. And the protons, the width of the beams, or the height of the beam, is on the order of, I think, 10 microns. So they're actually fairly small. Now, and so you have these two 10-micron beams passing through each other. But what happens is that you're right, that the probability for any two protons to interact with each other is very small. So we have to have lots and lots of protons in each of the bunches, and then have the bunches cross each other many, many times in order to get the rates. But actually, one thing that's interesting is that even so, it turns out when the LHC is running at its fullest, at its maximum rate, that the number of protons interacting at the same time, there will be multiple proton interactions at the same time, which will actually make the analysis very difficult or challenging.
And also you mentioned that you were needing students. Need any high school interns?
I had a high school student. A high school student has worked with me to develop some software to visualize these things. So if you want to take a look, actually over here in the 3D, what's called the cave on campus, you can stand inside a LHC event and watch the thing kind of swirl around you. So if you're interested in things like that, come talk to me.
I'm going to thank Dr. Chu now for his most informative talk. It obviously interested you so that it produced a great many questions. So thank you, Dr. Chu. And we'll now have a brief introduction to next week's talk, I hope. Well, I'll start.
Research is transforming our understanding of the universe and ourselves. The UA College of Science invites you this spring as scientists describe their world-class explorations into bioscience, artificial intelligence, and the hidden workings of the human brain. Come preview the discoveries we'll be making next. Join us Tuesday, February 10th for an intimate look at the next great leap for bioresearch, the iPlant Collaborative. This free lecture begins at 7 p.m. at Centennial Hall on the UA campus. See cos.arizona.edu.
Next week's talk crosses a boundary between physical sciences, astronomy and physics on one hand, into biology, and there is a real difference in scientific method in these two areas, because in physics and astronomy there are relatively few facts that we generate, and so when we have a chance to see something new, we leap towards it, try to make enormous devices like big telescopes or big colliders to try to generate something new so that hopefully we'll have some new kind of fact. Biology is different in that it is absolutely swamped with information. And so when you try to do something in biology, you don't try to get new facts, you try to make sense of the facts that you've got. In both cases, there's an awful lot of stuff that's in your way, stuff that you call noise, things that you don't want to know about, and you use a computer to get rid of them. For physics and astronomy, the big devices, the machines that produce the new information, take your attention, but behind them are sitting these enormous banks of computers to analyze the data. And so it's necessary to have that for biology too. But in biology, you just don't need to have a new machine ahead of it. And this is why the next talk will focus on a $50 to $100 million project that is largely about computing with the information that we've got in biology. It takes one of the areas of biology, the area of plants, and plants are important. They use solar energy, and they are the way, therefore, that energy gets into biological systems. They include at the small end things like moss, and at the large end things like giant sequoia trees. In the middle, you'll find things like potatoes, lettuce, and oranges, things that animal life eats. And you'll also find the Venus flytrap, where the plant kingdom takes its revenge and eats us. You'll also find that there are plants that are useful, producing stuff like rubber. You can get drugs and various other chemicals out of trees. The tropical rainforests are incredibly important, not only for their biological diversity, but because they anchor soil, and they convert a lot of the carbon dioxide that we put into the atmosphere back into oxygen for our use. So plants are a very important area, and they are the topic that has been funded to this level. To understand what is going on, you have to realize that we humans ask questions. We tend to have an insatiable curiosity. So we ask, how does it work? How did it come to be? How does it fit with everything else? And is it useful to us? Biology, as a science, approaches these tasks with some great syntheses. It asks questions like, how does it work, and translates that into molecular biology. It asks it questions how things came to be, and he calls that evolution. It asks how things fit in with everything else, it calls that ecology. And questions of usefulness, it calls agriculture. So all of these areas are indeed discussed, and the topics need to be brought together with a huge database and tools so that people can use it. And these tools will include computer encyclopedias and chat rooms and so on. It will be very important, not only for the researchers, but classrooms will be able to be involved as well. And it reaches across a huge number of disciplines. At the University of Arizona, there will be 8 different departments crossing 3 colleges involved in this project, and 5 other universities will be involved as well. But the work will, in fact, feed data worldwide, so it will be incredibly useful to everybody. One researcher put it, everything is connected. As our climate changes and our environment changes, we need to have a deep understanding of the biology of plants to adapt as best we can and to focus our efforts on saving the organisms and ecosystems that are most important to save. The talk will be next Tuesday, 7 p.m. here at Centennial Hall. And again, I would like to thank the sponsors of these talks for allowing us to enjoy them in comfort. Thank you.